This is Cosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen, to Cosmographia, the Randall Carlson podcast. And we are joined, as usual, by the usual cast of suspects. Bradley, how are you doing, sir?
I'm feeling unusual.
Feeling unusual. Not a usual cast, but an unusual one?
Nope, got to break away. Maybe just today, though.
All right. Silent Mike. Staying silent. All right. Randall.
Yeah, so Mike is feeling normal.
Brad
is feeling unusual. I'm sort of feeling abnormal.
All right.
But
That's
hopefully I'll get over that before the show's over.
Well, you usually do.
I usually do.
Yeah, I think so. I feel normal. I mean, it's a normal day over here in weird Snake Bros territory, so. Yeah.
A normal day. But you guys didn't have a normal day here last episode, did you? Or was it the episode before where everybody was struggling
we were about to
remain
fall asleep.
conscious?
Oh yeah.
Yeah, that was two.
Yeah, we were in the depths of harvest and got up at 4 a.m.
Yeah.
Worked all day and then came home and did Cosmographia. And so, yeah, it was great subject matter, but
which we'd all been waiting for.
Yep.
Lake Hind and the connection between cosmic and flooding. Yeah, we were waiting on it. And
I was like, I've been waiting for this.
I did not make it.
Well, you made a gallant effort anyway, even though at moments you failed abysmally.
Yeah.
that's why it's recorded.
That's
we can
right.
Go back
we can go back.
Review.
Yeah, we go back.
And I have.
Yeah.
Well, you guys got up at 4 a.m., right?
Yeah.
To do your harvesting grapes.
That's why we're up at 4.
Yeah. And so it was that and not that you were bored with the subject matter.
Absolutely right.
That's right. Yeah. Of course.
No, we'll let you know if we get bored.
Okay.
We'll tell you.
Because we don't want to be bored.
Randall, this is boring. Move on. Moon.
Well, I wasn't up at 4, but I had a long day also. But yeah, we were going. It was almost 1 a.m. at that point. So for you guys to hang in with that, kudos.
No, none of it's boring.
None of it is boring. That's right.
Well, unless we're talking about, taking borings for core samples.
That's true.
Yeah.
That's, I guess, the exception. Because those can get pretty interesting sometimes. Because, in fact, last week we were talking about borings from the sedimentary bottom of Lake Hind and what they revealed at minus roughly 33 centimeters, which was nanodiamonds, microspherules, the signature of something, right? But we'll come back to some of those questions because we certainly aren't through talking about nanodiamonds. That's going to be an ongoing, because studies are ongoing. And when those studies come out and they bear on, a deeper understanding of this whole phenomena, of course, we have to look at it. Like we haven't looked at the studies yet from the Alps. We haven't looked at the studies from Patagonia. We haven't looked at the studies from Antarctica. And these are really interesting things. So we're going to come back to catch people up along with ourselves on these some of these more recent studies from the last 2, 3, 4 years that have really extended the range of the deposition of extraterrestrial exotics to the Younger Dryas boundary. But right now we've been talking about the possible consequences of an impact because we're segueing over into the subject matter of megafloods. The thing about the megafloods is that as I've been sifting through the literature on megafloods for about 35 or 40 years now, one of the things that really strikes me is that there's no coherent theory in the sense that when we're looking at these catastrophic outbursts, whether it's in the Hudson River Valley or the Connecticut River Valley up in New England, whether it's connected, with the Finger Lakes of New York, whether it's Grand Valley of Michigan, whether it's the St. Croix River between Minnesota and Wisconsin, whether it's the outlet of glacial Lake Agassiz, whether it's the great spillways in the Midwestern prairie regions, whether it's the Channel Scablands, et cetera, et cetera, et cetera. There's no coherent theory that puts all of this together and ties it into the general process of deglaciation. Because if we go back to 15,000 years ago, 16,000 years ago, we're back right there at the threshold of the LGM. Right? What is the LGM?
Last glacial maximum.
Yeah, or late glacial
late glacial maximum. Right, close enough. Kyle, whatever your name.
I'm getting there, buddy.
Whatever the guy there to the left of Russ. That guy, yeah. The late glacial maximum. Right. So now late glacial maximum starts to ameliorate. Ice starts to retract. As it does its melting, as it melts, it creates lakes. It creates, it augments the flow of the rivers draining the ice sheet. Because, if the ice is expanding, right, it can't be draining. In other words, the amount of meltwater draining away from the ice sheet has to be less than the volume of ice that's expanding,
accumulating
as the ice is growing. Because, if we go back 25 to 30,000 years ago, we're looking at a couple of small nuclei, the Keewatin and the Laurentide nuclei on each side of the Hudson Bay that started growing, like the blob taking over. There was two of them, and they essentially grew and around the ice accumulated around these nuclei that eventually converged to form one much bigger blob of ice, and then that continued to grow. And then over far to the west, 1,000 miles to the west, 1,500 miles to the west, you've got the Cordilleran ice sheet, which is growing in its environment. And it basically started as montane glaciers, or glaciers up in mountain valleys. And if people know what a cirque is this sort of bowl-shaped carved feature that you see in a lot of glaciated mountains. And we can look at some pictures of them, and will be, as we go along here. But so you have this accumulation up in the mountain regions. It flows down into the valleys, and then those mountain glaciers coalesce in the valleys, and then the ice piles up, and those valleys will grow down, and eventually enough ice comes that it completely buried the whole Cordilleran region, other than just the very top peaks of the mountain ranges, the Rocky Mountains. So you had 3,000, 4,000 feet of ice, maybe more, in those mountain valleys. And that blob of glacial ice grew. And as it grew, it moved out. Now, bear in mind, as this ice blobs are growing, sea level is shrinking. As sea level is going down, coastlines are retracting, right? Now here comes the glacial ice moving right into that coastal marginal area where the coastline is retracting. Same thing happened even on a greater extent on the east coast of the United States, because the east coast continental shelf is much shallower. So as the ice mass grew, sea levels drop. As sea levels drop, the coastline retracts seaward, and the glacial ice is just following in its wake. So it's almost like the glacial ice is growing proportionately to the contraction of the oceans. See, now you reverse the process. Now, of course, when the ice sheet is growing, there has to be reduced melting, because if there wasn't reduced melting, the ice wouldn't be growing. It would be, if you've got the same amount of ice accumulating as the meltwater discharging off the ice sheet, then the ice sheet's going to be more or less stable, right? It's not going to grow. It's not going to shrink. If you have more accumulation than you do melting, the ice sheet grows. If you have more melting than you do accumulation, the ice sheet shrinks. Makes sense, right? When you think about it, right? So the ice sheet started shrinking about 15,000 years ago, or maybe closer to 14,006, because remember, 14,006 is the current date for the first big meltwater pulse. introduced back into the oceans. So there's something that happened around 14.6 that it definitely is worth looking into further.
But it could be a decrease in accumulation as well as an increase in melting, right? I mean, those two things.
Yes, but the critical thing is the ratio between the two.
Yes, right.
That's right. The critical thing is the ratio.
Because they could still be melting a lot, but if accumulation increases a whole bunch and overcomes the melting,
that's exactly right. That's exactly right. See, so now what you're talking about, though, is the implication of that is an accelerated hydrological cycle.
Yes.
And when we look at how rapidly the ice did accumulate, it really does seem like for, a period of 4,000, 5,000, or 6,000 years, the hydrological cycle was on steroids.
Right.
And then just about the time it reached its maximum, it started contracting again. But then that contraction process got interrupted, apparently, on at least 3 different episodes, 14.6, 12.9, and 11.6, give or take 50 years or so on each of those dates. So what happened? I don't know. That's what we're working to find out. And a lot of people are very interested in that because, as we've said over and over again, that perhaps was that period of time of 3,000 years was probably the most significant period of time of the last 3 or 4 or 5 million years in terms of concentrated global environmental climatic change. And within that 3,000 years, it appears that perhaps the Younger Dryas boundary at 12,008 to 12,900 was the most significant event node within that 3,000 years from 11.6 to 14.6. And this is where the nanodiamonds have been found, where the microspherules have been found. Now, I'm very curious about what happened at 14.6, 14,600 years ago. Could that have been an impact? Well, I know of no discovery of microspherules or nanodiamonds there that would be consistent with an impact. But here's the but. If you got, for example, on the ice sheet surface, when it's being melted away, right? And if you've got a lot of surface melting, well, you're not going to have any preservation, right? You're not, let's say the whole ice sheet gets dusted with microspherules, cosmic dust, whatever, right? If it's enough, it's going to change the opacity or the albedo of the ice sheet. So that's a possibility. We do know that right around the Younger Dryas boundary, there was several or perhaps multiple very large volcanic eruptions, right? There's evidence of that. In fact, there's evidence of that in Hall's Cave with the osmium isotopic ratios, right? We looked at that and said, well, yes, we've recognized that there have been volcanic eruptions clustered around the Younger Dryas boundary. We've known that for decades, right? The fact that you find the signature of a volcanic eruption in the deposits in Hall's Cave doesn't necessarily mean that an extraterrestrial event wasn't part of the mix, right? But the thing is you've got that layer, let's say, on the ice, and now you've got a period of accelerated melting. Well, any of that material that's going to have been deposited on the ice, that's going to be lost, presumably, if it melts away. But why wasn't the layer lost at the Younger Dryas boundary? Unless, of course, there was enough rapid freezing that layer was more or less preserved, or maybe only a few centimeters of it melted, and it wasn't enough to completely wash away the evidence. Maybe if you were there, at the time or right after it happened, perhaps the concentration of extraterrestrial markers would have been a lot denser than it is. But then we have the 11.6. And so what happened there? I don't know. But I think that we're kind of looking at this whole 3,000 year period here and seeing that it almost took this whole concentration of these events in order to successfully reboot the planet from what it was in the Pleistocene to what it is in the Holocene. So
it is odd that there's no meltwater pulse at 12.8 at the YDB. It would probably be a slam dunk for the impact hypothesis if there was.
Well, yeah, and I'm not sure that there's not. I'm just thinking if there haven't been the studies necessarily that have identified a meltwater pulse, because certainly, as we're going to see, in the next few episodes, there was a whole lot of meltwater introduced into the oceans right at the Younger Dryas boundary. I mean, the dating for the draining of Lake Agassiz is right now Younger Dryas boundary.
Right.
That would have been a significant influx of meltwater into the world oceans when that thing drained. So, if we pull up, so we talked about, let's see, I'm looking at Brad's map there. If we look up on Bradshaw with Lake Winnebagosh up there, right behind you. Yeah, right up there. That was part of the basin of Lake Agassiz right there. In fact, that's left over from Lake Agassiz. I think I have a, let's see here. Yeah,
couldn't they take ocean cores like from the bottom of the ocean and kind of do the same thing they do with lakes and ice, and kind of look at like if there was an influx of so much fresh water?
Mm-hmm.
I mean, I know that this is the bottom of the ocean, so the saltiest water is, it's more dense, but it might have had some effect. Could they tell from the layers in the bottom of the ocean if there was a big pulse of fresh water into the ocean at that time?
Well, yes, because if there is a pulse of fresh water, especially if it's gone over a land surface, it's going to pick up a lot of biological material.
Yeah.
It's going to have, and you're going to find that. And also you're in the Heinrich layers, this is when the icebergs are discharging. When you have a highly active ice sheet, it's discharging large numbers of icebergs into the ocean. And those icebergs are, they're loaded with coarse material, gravel and sand and so forth. And then those, because in your deeper ocean, the normal deposition is just going to be this little diatomaceous stuff, very fine grained, right? And then suddenly you've got sandwiched in there this very coarse material. And then that's overlain again by normal, very fine grained deposition. And then there'll be successive layers of these successive coarser layers. And by analyzing the composition in these layers, they can determine where they originate. Where did the rock, because there's pulverized rock in there. And so where did this come from? Well, it came from the Canadian Shield. So clearly, it had to have been transported by ice, and that makes sense. If the ice is growing, it's grinding over the land and picking up material, and it reaches the coastline, and it, the edges of the ice sheet calve into the ocean as icebergs. Those icebergs then begin to drift south, and as they drift south, they melt, and as they melt, that material that they're carrying, that coarse material, then falls to the bottom of the ocean and forms the Heinrich layer. And those things can be dated because, for one thing, you've got biological material, you've got marine, you've got benthic and planktonic species that are sandwiched in there that can be dated, the little forams and so forth. So you've got the normal ocean bottom deposition, and you've got the coarse layered Heinrich. Then you've got another ocean bottom. In the Heinrich layers, they tend to be very deficient on datable material. But they're sandwiched between layers that do have datable material. See, so you can kind of create this chronology. And I'm not up on the latest. Something to be worth investigating, because that is a very powerful proxy for global and environmental change right there. So in this long rambling, I was about to make some point, which I've completely forgotten.
Apologies, my friend.
So we were talking about Lake Hind and the finding of microspherules and impact proxies in the sediments that were at the bottom of this lake that undoubtedly formed between 12.9 and 14.6. That's another point to emphasize, because at 14.6, we've got some accelerated melting that goes on, so the ice sheet is contracting back. As it contracts back, it creates proglacial lakes that are composed of meltwater, right? As the ice continues to shrink, the meltwater continues to accumulate, right? Now, because the ice sheet has been so thick, the isostatic depression around the core of the ice sheet has depressed the land surface maybe 1,000 or 2,000 feet, right? So now you almost have it sitting in this bowl. Let's see. there we go, a bowl, and you've got the ice sheet there. But as it's shrinking back, the water's accumulating in that depressed area. And so what you have is this shifting ratio of glacial ice to proglacial meltwater. Well, as this meltwater flows away, as the ice melts and the meltwater flows away, you now start to get isostatic rebound. So you have to now start factoring in these isostatic effects, because through the isostatic rebound, it's now coming up. And as it's doing this, it's causing spillovers. So you've got a drainage divide that's keeping the water accumulated around the glacier margin. Well, when the depression or the bowl rebounds enough so that water rises up and spills over the drainage divide, it's now being dumped, say, into the Mississippi River. Like, this was one of the theories for the cooling of the Younger Dryas, was that as the ice retreated north, it had been discharging into the Mississippi River Valley and therefore in the Gulf. It receded back far enough that the drainage shifted from the upper Mississippi watershed. It shifted east and started flowing into the St. Lawrence. When it did that, it flowed then into the North Atlantic, and all of this cold, fresh meltwater went in there, and it interrupted the circulation, the meridional
thermohaline.
Yeah, the meridional circulation. And so now, because it interrupted that, because the amount of water was so voluminous that it just actually caused the circulation to stop. So the circulation, as it's coming up from the equator, is delivering heat to higher latitudes like Europe. And so the theory is that Lake Agassiz overflowed into the North Atlantic. It caused an interruption of the meridional overturning circulation, and then that interrupted the delivery of heat to Europe. Europe cooled down, and you had a return of tundra flora and fauna to northwestern Europe, including Younger Dryas octopetala, which was the polar wildflower that came back again right after 12.9. So that was the idea. But then I go, okay, it makes sense as far as it goes, but the problem is you've got this inland ocean of fresh water that's meltwater. That's not there's more to the story. There's more behind that. You can't stop there. How do you get this gigantic mass of meltwater that was Lake Agassiz? That's a question that I think needs to be asked. So now we come back to this idea of accelerated melting. So I think here's the model as it's now more or less, is that around 14.6, there's a short period of accelerated melting. And then it went into a warm period with continued melting, causing the ice to shrink back. And this exposed a lot of the land area around the southern margin of the ice sheet that had previously been glaciated during the LGM. And it receded just as far as where Lake Hind is, basically. So Lake Hind would have been right there at the southern margin of the Laurentide ice sheet after it had contracted back after 14.6. And so there's this body of meltwater there at 12,012.9. And at that point, now you had this influx of extraterrestrial material. The material settled to the bottom of the lake, and more sediment covered it over, and it got preserved more or less. Now it's core samples have been taken. But what we're getting to with this thing is the whole melting sequence. And so we had this, I'm working on a colorized version of this, which I'll have hopefully by next episode, but I'm gonna pull this up anyway. Let me get it up here. So I'm not actually finished with it yet, but it will be still worth looking at. So we will do a share screen here. Okay, so I've colorized Lake Hind to make it really easy to see. And I'm just still working on Lake. Would be part of, this would have been the western shore over here of Lake Agassiz. I'm going to, this blue color needs to extend right down in here. And then, of course, Lake Agassiz extended to the east all the way up to the edge of the ice sheet. And then you had this series of these lakes that had formed in this area, this kind of low area, this swale here between the Missouri Escarpment you see on the west and Lake Agassiz on the east, and then the ice sheet margin even further to the east. But what you had here was this whole series of these huge interconnected lakes, and these lakes apparently drained in succession. The exact chronology is still being worked out, but in the process, these huge spillways were formed. We have the Pembina spillway here. Then we had the Souris spillway coming down here out of Lake Regina. We have the Des Lacs spillway, the Moose Mountain spillway, the Pipestone spillway, the Croix Appel, if I'm saying it right, which I'm probably not, spillway, the Cut Arm spillway, the Assiniboine spillway. Now, these are all very large valleys relative to the rivers that are flowing in them. And so what we're looking at here is actually trying to decipher and put together the whole sequence of events that created this complex of these huge spillways. Now, to get a sense of the spillways, I'm going to have to probably stop the screen share and start it again. We started looking at some of these features last episode, and looking around, share screen again. Here we go. All right, so here is Oak Lake, which is the remnant of Lake Hind. This was the Lake Hind Basin. And right up here, we see the Assiniboine River and spillway right here. And if I, let's see, we've already covered this, so I'm going to go right past this. So here's a closer in look. And this, as we introduced in the last episode or two, this idea of the underfit river. It could also be an underfit creek, but the idea is the same: is that the water flowing within this channel is minuscule compared to the size of the channel. And, the old uniformitarian or gradualist argument might be, well, that, over millions of years or hundreds of thousands of years or whatever, the river that you see here will eventually cut this channel. The problem is that you go back 15,000 years ago, and all of this was completely obliterated. The former landscape was completely obliterated under 1 mile to 2 miles of ice. So this channel formed in tandem with the melting away of the ice sheet. So it wasn't something that took, tens or hundreds of thousands, or even millions of years. It was something that took place over a very short period of time, a few years or a few months or even less. All right. But you can really get a sense of the scale here. This channel here is right here, and this point is about a mile and a half wide. Right. And so you can see these side valleys coming in, these tributary valleys, they can be no older than the main spillway channel, right? You're not going to have these tributary channels flowing in off the uplands to the lower elevation spillway if the spillway isn't there. You got to get the spillway, and then you can start cutting in these secondary tributary canyons. Make sense, Russ?
It does.
Okay,
I was going to ask you about those. Do you think they formed along with the channel, or are they later?
I would say they probably started forming immediately. I would guess that they formed very shortly after.
Okay.
Because you're still going to have so much residual meltwater that's going to be draining off the uplands.
Right. Okay.
So I would say that
torrential rains,
right now they're being subjected to more gradualistic erosion, if at all. I would have to go there and determine. I mean, if they're once they're taken over by forests, the erosion pretty much stops, unless you had a really catastrophic flood that was powerful enough to wash away the forests, which are extremely rare. But that's the scale of the floods, of course, that we're looking at here. And there are examples. We can see modern examples where they've been concentrated. The James River flood of 1969, when the hurricane Camille, thank you, Camille, stalled over Virginia, and you had such a drenching of the headwaters of the James River that you had creek valleys where the whole forests were basically just washed away, trees, roots, and all. But that was a really exceptional event.
Right. So those could be formed by torrential rains during this.
Yeah.
Period.
Yeah, absolutely. And again, water draining off the uplands could be both directly meltwater, and it could also be rainwater. Yes.
Right.
The idea is you've got accumulated water on the uplands, and once you have the channel cut, see, typically what you're going to see is the process here oftentimes is you'll have a sheet flood. It's kind of spread out, and it's going to be shallow, it's going to be wide, it's going to be moving pretty fast. But if there's a zone of weakness that water can exploit, the water wants to, it's trying to like converge, it's trying to pull itself together as much as possible. So if there's a zone of weakness, it's going to exploit that, and it's going to begin to accelerate the erosion of a select region within this sheet flood. Well, once it does that, it in this, let's say the inner channel begins to grow, then the proportion of water that's composing the sheet flood increasingly becomes concentrated into that growing channel until eventually, at some point, the channel could capture the entire volume of water that started out as a sheet flood. Does that make sense, Russ?
It does.
Good. Because if it makes sense to you, it's going to make sense to just about anybody, right? Okay, so.
Thanks.
Okay.
So how deep is that, Randall? You said it was 1.5 miles across right there at the.
I think it's about 400 feet deep.
Wow.
Maybe in some cases, but maybe 200 feet. Part of the thing, though, is you got to remember is that the valley floor is not maybe the full depth because there's maybe, many hundreds of feet of sediment accumulated on the bottom.
Right.
And that's indicated by, look at the meandering nature of the river. Yes. Those meanders are because they're just cutting through this easily erodible sediment that accumulated on the bottom of the spillway. So that sediment could be very thick. And the spillway.
And a lot of that river's probably also flowing in that sediment underground.
Yeah.
That's the way it does here. There's a lot of places in the river where it just
disappears.
You don't see the river because it's down in the gravel, in the sediment, and it comes up downstream.
Right. And then I think we hit upon this, but it's an important point that this minus 33 centimeter in subunit B1, the mineralogical and elemental evidence supports the occurrence of the Younger Dryas boundary cosmic impact event. Including concentrations of magnetic microspherules, a distinct peak in nanodiamonds, anomalously high concentrations of platinum, iridium, and anomalous concentrations of chromium, cobalt, thorium, uranium, hafnium, scandium, and lanthanum. The high-temperature magnetic spherules exhibit morphologies and chemical compositions like those found in sediment dated to the Younger Dryas onset at approximately 40 other sites across nearly a quarter of the Earth's surface. This evidence is comparable to distal ejecta from known impacts and inconsistent with non-impact terrestrial mechanisms. I like this. It's worth repeating so people will think about this. If the Lake Hind area was influenced by a high-energy ET event, such as the ablation or atmospheric burst of a fragmented comet or chondrite, this may have produced a high-energy seismic pulse, or less likely, a thermal pulse that briefly increased surface temperatures. And I'm not sure why that would be less likely, because we do know from the limited number of examples that we have, Tunguska, etc., that the thermal pulse can be pretty damn intense.
Yes.
Tunguska, 200 square miles of forest was incinerated in the thermal pulse. So, but in any case, either phenomena may have led to release of meltwater into regional drainage systems through destabilization of the Laurentide ice sheet margin, including failure of glacial dams upstream from Lake Hind that were holding back proglacial lakes. So if we go back, notice here, the Pipestone and the Qu'Appelle and the Assiniboine, they are flowing into Lake Hind from these lakes. Here we have Lake Indian Head, Lake Saltcoats. So these glacial lakes, meltwater lakes upstream, are flowing into Lake Hind. Then we notice that these two outlets here, this one flowing and discharging right at Brandon near the Assiniboine fan. So this is the fan. This is just wash, that's sedimentary wash that's been carried in. Picture, if you've got a flow of water and this water is loaded with sediment, the faster the water is moving, the more sediment it can carry. The slower the water is moving, the less sediment. So if something accelerates the velocity of the water, it can potentially carry more sediment. If something decelerates, then it can't carry as much. We call that the competency. Its competency to carry sediment diminishes. So then what it has to do, it has to begin dumping some of that sediment. So if the flowing river or creek flows into a standing body of water, what happens? It slows down, and it begins laying down its sedimentary cargo. And this is what builds the fan. See, and that's what we see right here, this Assiniboine fan. And then we have the Pembina spillway flowing out of Hind, which then also flowed into Lake Agassiz. But then we have we have Lake Souris. Now, it appears that Lake Souris was flowing into Lake Hind because of the isostatic depression that caused Lake Hind to be lower than Lake Souris. So I will stop there.
So did all that used to be under the ice at the full extent?
Yes.
Okay. So some of those systems may have begun forming before the ice had even fully retreated off the top of it, right? All those depressions and pathways.
You mean as subglacial flows? Yeah, I don't see any reason why that couldn't have been a factor.
Okay.
For sure. So then we were talking about these spillways, and let's go back to this. And here, I'll do another screen share.
If we're going off planet, we might be a good place to take a break. If you're going to start something new there, but yeah, if you're still
you're probably right. That's good. Good place to take a break, and then we'll get on to here talking about the spillways and more of the mega flood features and how to recognize them. What we're looking for.
Okay, sounds good.
Yeah. All right.
And we are back, ladies and gentlemen. Cosmographia Podcast. And real quick, before we get back into the subject matter, we're going to talk about CBD from the gods. Give an update. So how's it been going for you, Randall?
Oh, I have nothing but good things to report at this point. Things are going well, and I'm sure I'm attributing a large portion of that to this regular use of the CBD oil, both internal in terms of the droplets that I'm doing under the tongue, usually before I go to bed, but I'm going to experiment with it and do like maybe half a dropper during the day and then half a dropper at night. And I did do, what was it, 4 or 5 days ago, I did 2 droppers. And I would go, okay, well, what's my limit? And I felt like 2 I didn't need 2. I thought I'll stick with 1, maybe 1.5. But, I started out with half a dropper. What are they, 30 milliliters each?
1 milliliter per dropper is 30 per bottle.
30
full
per bottle,
yeah.
So, but the thing, the new development is, I told you about Julie was an electrician for 30 years. So she, lots of wrenches and screws, constantly turning stuff. So it really left her, she got her wrists and hands got kind of arthritic, so she was having very trouble gripping stuff. Well, she's been doing it for about a month now. And what she does is she'll get the salve and she'll put a glob of it on her hands, and then she takes that and works on my back with it. So it's like we're killing 2 birds with 1 stone there. It's a good method that we've worked out. So, I'm going to continue to do it, and hopefully, continue to experience benefits. I was already convinced before I started using this particular brand that I really wanted to get into an experimentation and long term to see what effects the CBD oil could have. And I'm glad that the timing of this was good. It seems like, everything I've been learning about these folks out in Oregon, it's their, their hemp is some of the best in the world that they grow there, and they really believe in this. It's not just about making a whole lot of money. It's about really creating a really top-notch product. So as I've been looking into that and where it's coming from and the people that are doing it, I'm liking that side of it too. So overall, the experience has been really good, and I'm going to continue to experiment with it and see where it goes from here. We still haven't, Brad, you still haven't tried massaging any into your scalp yet. I'm waiting to see what happens when you show up one day with an afro.
If they give me a barrel of it, I guess I'll start. But other than that, I'm not going to waste it wishing.
No. Hoping for
I've dealt with it for 20 years, I guess. I'm not going to fret. I've been doing the half and half. I've just kind of started that. I was doing a half a dropper during the day, and now I've started doing the other half before I go to bed. So I don't really know the effects yet. But the idea of doing the kneading it into your back. I mean, there is a sense that just massaging those areas though is good. Whatever you may be using,
sure.
Just for your circulation, just to be rubbing those areas is going to be good regardless. But having a salve that's also on there that's doing something is doubly or whatever, triply good. But yeah,
I think so. And then I think I said in the last episode we were talking about, this was about 2 weeks ago. She'd been doing it for a couple of weeks. I came into the kitchen and I think it was a jar of pickles. She was opening a jar of pickles. Well, for probably the last 3 or 4 years, if she needed to open a jar that was vacuum sealed, she would call me because she didn't have that torque in her wrist. And she comes in there, I come in the kitchen and she's opening a jar of pickles. And I said, "Oh, I can do that." And she goes, "Oh, I got it." I said, "Well, wait a second. What's going on here? You just opened a jar of pickles. Something's happened here. And I want to know what's going on." She goes, "Oh, I did, didn't I? I opened this jar of pickles." And I thought, well, now you couldn't have done that, for several years. You'd have been calling me. I'd have been comfortably ensconced in the other side of the house or whatever. And you'd have been calling me. And I'd have to get up, walk over to the kitchen and come in there and open the damn jar of pickles for you. And you just did it. So what's going on here? And she goes, "Oh, maybe it's the salve." I said, "Well, maybe it is. So I don't know." But that was a milestone. Let me tell you, that was a milestone. That's a true story. And I'm just wondering if that's what it is. So I suspect it is, because that's the only thing I can come up with that's different.
One less thing on the honeydew list.
Yep.
Yeah.
I have the salve too. I haven't started it. I've just been doing the oil.
So do you have problem areas where you would use it, or you just, because I definitely have had these pulled muscles in my back and 2 back injuries, so I've injured my neck and had whiplash in my neck. And then I partially ruptured a disc in my lower back years and years ago.
Yeah.
So when they flare up, boy, the nerves just, but I think then what happens is the nerves cause the nerve inflammation causes the muscles to tighten up. And then that just kind of creates this vicious cycle.
Yes.
And if the muscles relax or the muscles get put at ease, then the recovery is a whole lot quicker.
Yeah. Yeah. I need to try it. I just haven't started trying it on my back. Yeah, I have a broken back, so
right. You broke your back.
Probably can't be fixed, but there are all like the muscle problems, like you just said.
Yeah.
So if it could ease some of that would be fantastic, because the broken back is way down low, but the muscle problems grew and they're all the way up to my shoulders practically. It expands from the area. So I do need to start trying it. But I tell you what, the oil is really improving my sleep. So
good.
I'm loving it.
Good news.
I need a case.
Well, yeah. Yeah. Well, I can see you now. We're out there and he's chugging bottles of the stuff.
I'm already looking at the bottle like it's getting empty. I'm going to need more soon.
Well, I think it's great. I think it's one of a whole new generation of medicinals that could evolve from plant sources and natural sources and things that I think it's a really, really encouraging development. And I'm glad we can finally get to experience the benefits of this, starting to get the benefits without having to worry, oh, I'm going to get busted and thrown in prison.
Yeah.
Definitely.
You know?
And if you order some product through the website, cbdfromthegods.com, and you can use a special code and you will get free shipping for Cosmographia listeners. So that code is RC ships free, and that's all listed in the links in the show notes and video description, so you can find it there.
Yep. It's good
Sweet.
stuff. People get it.
All right. So where were we, Kyle?
I thought we were going off planet, so I kind of interrupted, but maybe I was
you
not
were
right.
about to bring up some new slides and show us something. I don't know.
Yeah. Well, let's go back through really quick some of the slides we looked at last week, and then we'll move on to new ones. And to give folks the idea of some kind of the distribution of some of these great meltwater ponds that formed. So we'll just do another share screen, jump right into it.
Got it.
There we go. All right, you see Hudson Bay up there. Now, this is showing the maximum extent of the meltwater. You'll see that all of this big old this is Lake Agassiz here. I mean, look at this compared to the size of the Great Lakes. Now, if anybody or listener lives up around the Great Lakes or has visited, the Great Lakes, they deserve their name, the Great Lakes. But now look at Lake Agassiz. I mean, when you stand on the shore of any of the Great Lakes, you're looking out, you don't see the other side. You're just seeing an endless body of water. Now look at Lake Agassiz. I mean, that's a huge amount of water.
Yeah, that's like an inland sea. Probably.
That is like an inland sea.
Yeah.
And of course it's fresh water. And yes, this is a transitional phase that we're looking at here. And if we come down to, let's see here. Right here, you see this, you see Winnipeg, and then you come straight down to this southernmost extension of Lake Agassiz. This was one of the discharge points right here. And that fed into the upper Mississippi watershed via the Minnesota River. And I told the story of how the River Warren, which was the glacial meltwater flow that came down through what is now the Minnesota River, was the thing that way back in 1969, when I was standing on the bluffs, the 200-foot high bluffs, looking down at the modern Minnesota River, channel in its little channel with its own little bluffs on each side. And then I saw 3 miles away another set of bluffs. That was my first intimation of the idea of scale and variance. And I went away from there with this thought on my mind that, was this just a bigger version of that down there, that little river down there? In the Minnesota River isn't a tiny river by any means. But that stuck with me. It always stuck with me. And then, of course, I never really acted on it, or it was just a thought, like, okay. And then I quickly forgot about it. But I came back to it. Things would remind me of it, So there was a whole succession of things over the next decade that finally led me around to like going, okay, there's a story here, We go, I travel out and the next summer, and I go down through the Columbia Gorge, and I see all of these gigantic fans splayed out from the tributary valleys. And see, the thing is that on an unconscious level, I recognized what I was looking at because I'd walked as a kid, living in rural Minnesota. I had walked along many, many creeks and rivers and had seen that exact thing, that the fans splayed out from the mouths of tributaries coming into creeks and rivers. I had seen that, but it had never really registered. I didn't think about it. I mean, people walk along and they see this stuff all the time and you don't really think about it. Like going, oh, let's see. Well, there's a fan splayed out. This is sediment being carried by this tributary. It comes into this gravel bar, sand bar here, and it builds this. You don't really think about that unless you're a geologist or a geomorphologist. That, I think, is what distinguishes the geologist, is that's the person that looks at these things and thinks about them and wonders about how they were created. But my point is I had walked along many rivers and creek, sandbars, point bars, and everything along creeks, and had seen those features where the splayed out fan might be 3, 4, 5 feet wide, an inch thick, and it's coming out, and you can very clearly see it coming out from, you might be having a creek that might be, let's say the creek is 20 feet wide and you've got a smaller creek coming in from the side. And so it's discharging right there where there might be a point bar. So it's building this fan. Well, when I went through the Columbia Gorge in 1970, I was seeing those formations, but on this massive mega scale. And it just didn't register what I was looking at, but it was consciously, that is. Subconsciously, I think I kind of saw what I was looking at, but it was just the scales were so disparate, I wasn't making it a connection. It wasn't until years later that after I started reading Bretz and looking at and learning more about geomorphology and seeing aerial photographs and all of this, that I go, oh, wow, this is a scale invariant phenomena. And I've got pictures, and I'll try to gather some for one of the next coming up episodes, where I take pictures all the time when I walk along creeks and rivers, because they're like living natural hydrological laboratories. And you go to a sandbar, you can see recreated all of the forms and things that you see on a mega scale in terms of these mega floods. Because that's the thing about water erosion and deposition, is that you can have a cataract created by water that's 400 feet high and 5 miles wide, or you can have one that's an inch high and a foot wide. But the morphology is basically the same, because the principles are the same. It's the way water moves. It all comes down to the movement of water. And what water can do is it's moving over the earth, because it sculpts the earth. So going back to this image here, you can see the vast extent of some of these meltwater pools that accumulate against the receding ice. Then, if you also think about how the land is rising, what's happening as the land is rising is the water is now spilling over the divides, because the water's ultimately, it's using gravity, but it's all trying to get back to the main body of water and rejoin the ocean. We want to get back to the ocean. We want to get back and be part of the big amorphous body of water that's really a continuum around the entire planet, right? Unless it gets temporarily sequestered in the form of glacial ice or groundwater on the continents. But even groundwater, it's ultimately, everything's trying to get back to the ocean basins. And so
is that Hind just to the left of Winnipeg there?
This would be Hind right in here.
Yes.
Look, see, here would be Lake Regina or Regina. I think it's Regina. But actually, this is I don't think Lake Hind was ever this full extent. The maps that I've seen of Lake Hind, they vary somewhat. Because I think some of those shorelines that they're tracing might get kind of amorphous in places. But anyways, yes, Lake Hind would have been right in here. And then this would have been that connection back to Agassiz. To Agassiz. And these arrows represent flows out. So in other words, you've got to see these arrows, they're flowing back. So one of the theories, as I mentioned earlier, was you had a shift in the major discharge of Lake Agassiz into the upper Mississippi watershed. It shifted east. And then you'll see here flowing out this way up through the St. Lawrence Seaway and into the North Atlantic. So this goes back to Wally Brecker and some of his colleagues that theorized that it was this massive influx, this massive flowing of Lake Agassiz back into the North Atlantic that caused the shutdown of the meridional overturning circulation, the MOC, meridional overturning circulation. Got it? The MOC, Kyle?
I got it.
And it's easier to say MOC than meridional overturning circulation. So we'll call it the MOC. So it interrupted the MOC. And because it interrupted the MOC, it temporarily interrupted the transference of heat from towards the equator in the lower latitudes towards Northern Europe. Problem gets into the timing of that. And we can get into talking about that somewhat, why it perhaps is the idea doesn't curry the same favor it did a decade or two ago.
What other routes are there to the North Atlantic other than the St. Lawrence Seaway? I don't see that much is connecting to St. Lawrence. Is it going out through up into the Arctic Ocean?
Well, yeah, that's become apparent now from studies of the Mackenzie River Delta and there's a whole set of scablands and erosional features up where the Mackenzie River flows into the Arctic, and we're going to be moving up there. We're going to be looking at maps and stuff. So that's the third outlet, a northern outlet into the Arctic Ocean. Yeah. And that may have contributed to, causing a rapid cooling of the North Atlantic. But yeah, all of these arrows here are showing meltwater pathways. So look, you see you've got this pathway coming right here. Now check this out. There's Lake Nipigon right there.
Yep.
Right under that arrow. And it's showing that there's a massive flood. And this flooding right here has been dated right at the Younger Dryas boundary. So it's coming out this way, and you see the arrows coming here. So you've got this, and then you've got some water coming over here. Interesting, we'll come down and look at this. Right where this arrow is, that's Grand Valley, Michigan. So it's a huge spillway right in here. And then check this out, down here coming out of Chicago, down here. Look at this, Brad. This is where we visited. This is where the Kankakee Torrent would have been. And all that erosion, that really interesting and bizarre erosion that we saw there along the Illinois River. That was right here.
I see it.
Yeah, I know. It's pretty amazing, isn't it? And then right here, notice this arrow. Well, that arrow is the St. Croix. That's where we took Graham on the last day. We went out to the Great Potholes. And those potholes are in a constriction within the St. Croix River Valley where it comes between layers of hard basalt. And as that water comes focusing into that constriction, it has to speed up. It's the same idea of the conservation of energy. So as that water is coming through the constriction, at any given point past a measuring device like a weir, the volume of water passing there is the same along the run of the current flow, right? But if you've got a wide channel that where your cross-sectional capacity is much greater, it's going to be slower, right? But then you get up to a constriction. So now, since the same amount of water, the same volume of water is passing any point in the constriction or in the basin, the thing is, in the constriction, though, the water has to be flowing much faster in order that the same equivalent volume of water is passing a point within the constriction as it is a point within the basin. And this is an important property that you have to kind of get in your mind to understand this geomorphic alphabet, this geomorphic grammar, if you will, is because you see in a flow like this, you're going to have natural constrictions, you're going to have natural basins. So anywhere where there's a constriction, you're going to have flow acceleration, and then you're going to have, that's going to tend to be erosive. Then if you have a basin where the water flow spreads out, that's going to be a depositional basin. And typically, what you'll always see is the same, is that when it begins to deposit its material, it deposits the large material first, the clasts, if you want to use that term. It deposits the large material first, and then as the water is slowing down, there's a grading, a sorting of the material from coarse to fine. And that coarse to fine is a paleocurrent indicator. Right, Kyle?
Yes, sir.
A paleocurrent indicator. So we're learning about paleocurrent indicators so that when we go out in the field, we see a paleocurrent indicator and we go, oh, yes, the flood came from that way and it went that way. Right? Because what we're doing is when we're seeing the evidence for these big old current flows out in the field where there's little or no water flowing now, the question is, where ultimately did this flood start? If you've got, say, a reservoir of water in the case of like the Teton Dam failure in 1976, the dam fails, you got this big flood that comes down and it completely changes the landscape within its pathway so that the post-flood landscape is very distinctly different from the pre-flood landscape. But and you can go throughout that area down current from where the dam failed, and you'll find paleocurrent indicators, a bunch of different kinds of paleocurrent indicators. But if you raise the question and say, well, ultimately, where did this flood start? Well, you can go right up there and you can identify the reservoir. And so when we talk about, we mentioned this last time when we talked about Lake Missoula, well, the assumption is, oh, okay, well, look, we see all this erosion in the eastern Washington along the Columbia Basalt Plateau caused by these great floods. Well, there's no big floods happening there now, but so they happened, they're over with, and they created this landscape that you see now. Where did the floods come from? Oh, well, they came from Lake Missoula. End of discussion, right? But then I come along and I go, well, wait a second. You're talking about Lake Missoula. You're talking about over 600 cubic miles of water. Where did that come from? That had to have come from somewhere. And that's where we get, I think that the whole model of glacial ice dam and glacially impounded lake begins to come apart, because, you know, you're faced with this question. That's a very huge volume of water. I mean, it's almost filled the entire watershed. So you're up to first order streams feeding this massive lake. How is that even possible? First order streams are the highest. When you look at the hierarchical ranking of creeks and rivers, say in North America, number one is the smallest you can have. There's nothing feeding into it. It usually is starting from an ephemeral creek that only starts when it rains, or it's coming from a spring, right? So you've got the first order, it comes in, and then it meets another creek comes into it, or it meets another creek, and now you've got an enlarged creek, and that becomes a second order. And likewise, you can go right through the ranking. And when you get to the biggest river system in the North American continent, with the biggest watershed, with the largest network of tributaries, is the Mississippi. And Mississippi, I think, is order 12. You look at Lake, and now you look at any of the Great Lakes, and you start going, well, there's no Great Lakes on Earth today being fed only by first order streams. Because for one thing, then evaporation far outpaces accumulation of water. However, somehow Lake Missoula is defying that process, because you've got first order streams that are literally within a few miles of the watershed divide. Right? You come onto the western shore of Lake Missoula, right in the Bitterroot Mountains. You're right up there almost to the top of the mountains. It goes up another 400 or 500 feet, boom, and you're spilling over the tops of the range. Right? So you got to think about the rainfall falling. If you look at the ratio of catchment basin to lake, there's a considerable disparity. In other words, your collection area has to be pretty significant to create a great lake, unless you're looking at an exceptional event like we are here with this rapid melting of the ice sheet. But somehow Lake Missoula managed to accumulate 600 plus cubic miles of water. And then where it could have only been meltwater or precipitation.
And then it did that like 40 or 70 or 90 times.
Yeah. How is that even possible?
Yeah.
How is that even possible? How is it possible? Because assume it's meltwater. Well, if it's meltwater, that means the glaciers are receding, substantially receding in order to yield up that volume of water. Assuming normal glacial recession, which always proceeds marginally, right? Although in this case, in what we're looking at here, these floods of meltwater did not really start marginally in many cases. They seem to have had melting epicenters well removed from the glacier margins. So, this is the question that we're going to really be getting into when we start looking in depth at the Missoula. And what we're going to do is we're going to work our way around the continent, looking at these great flood features as they're distributed over the North American continent.
So is it possible that Lake Agassiz may have actually looked like that with ice to the south of it? If impacts caused the melting, right? It could have actually looked somewhat like this picture, where there's this gigantic meltwater lake with ice south of the water. Is that possible?
Well, here's the thing. There probably was ice, but it was most likely stagnant ice. That is dead ice.
Right.
And this is something we're going to, again, explore in detail, because there seems to be a major transition in the ice between living glacial ice and stagnant dead ice in the aftermath of something, right? Because as we talked about, glaciers I think of them as alive. They're accumulating. They're like slow moving rivers, but they're an integrated mass of ice that's flowing along, right? Coming down, and as it accumulates in the zone of accumulation, then it's ablating or melting away in the zone of ablation. Typically, there's always a slight fluctuation, but there will be a period of time where you're more or less in balance. Sometimes it'll be shrinking back. Sometimes it'll be coming forward. When we go back to the Little Ice Age, say between 1400 and 1800, what we find is that many of the glaciers around the globe grew to the largest extent they had been since the end of the Great Ice Age. So we are literally coming out of a period of, and it's rightfully called the Little Ice Age, right? And we know this because we can see the moraines, the terminal moraines left by the great ice sheets. When mountain valley glaciers come down and they create the moraines, the arcuate, say if it's a terminal moraine, it tends to be arcuate because you have the glacial lobe tends to be tongue-shaped, right? And the terminal moraine is the material that's been essentially shoveled up or conveyed through the ice and dumped at the mouth of the glacier. So then when the glacier begins to recede back, it leaves this very distinctive pile of glacial till or rubble, right? So we can see the Little Ice Age moraines, and we can see the Big Ice Age moraines. And the Little Ice Age moraines were the biggest ones in pretty much 12,000 years.
So it was little because it was short, not because it was less ice, basically.
No, there was less ice, way less ice, but it was still more ice than there had been throughout the entire Holocene. But see, that's what makes the Holocene so distinct from the end Pleistocene, is that at the end of the Pleistocene, you had double the amount of ice on the Earth than there is now. That's why sea level was 400 and some feet lower. See, but the point is that, you know, when the ice is melting back, it's gonna pool water just like you see here, right? What to me is not known is ultimately what triggered this, you see, and that's where the impact hypothesis gets so interesting as a possibility, as a candidate for triggering. The other is solar activity, and I think it could be some combination of both. And we're going to get into that, why I think that an influx of extraterrestrial material into Earth crossing orbits may also affect the activity of the sun. So that's where I think that it could be fruitful to look at the 11.6 or the 14.6 melting events, because to my knowledge at this point, as we've iterated and reiterated, we don't yet have identifiable impact proxies at those horizons. So right down here, this where this bottom arrow is, this is meltwater draining from Lake Agassiz into the Minnesota River system, right? And right at that mouth, there's a lake at present called Big Stone Lake.
Can I jump back for a minute, Randall, just to complete a thought there before you share some of the pictures? Maybe you skipped it on purpose, but Russ commented about the lake refilling 40, 50, 60, 70, 90 times, right?
Yeah.
And and we're talking about a 500 to 600 cubic mile lake.
Mm-hmm.
Okay, so you're asking, where's all that water coming from? So if it's rapid glacial melt to fill that lake, the other part of that problem is, how is that going to have an ice dam or a lobe of the glacier advance down the Clark Fork River and block that valley to build up the lake? So that's the second part of the problem with there being 70, 80, 90 floods to back up that much lake water. If it's melting, it's warming, and that lobe is not going to block off that river valley repeatedly.
That's precisely it, Brad. Exactly.
Yeah. It could have been dammed up the first time, but then after that.
Yes, and I think yes again. I think that there was a dam there temporarily, and the water backed up against the dam temporarily. But somewhere, once the water in the Clark Fork Valley and throughout the entire basin had to get to 4,200 feet above sea level. So that is phenomenal. I mean, when you're in the Clark Fork Valley and you're looking at that 4,200 ASL, and you're at 2,000 feet above sea level, you're looking at something that's 2,000 feet over your head, and trying to visualize how the hell that much water got in there, right? It's problematic. And what Brad was just saying is, well, isn't that a contradiction? Well, if it's meltwater, that means that the ice is melting back, right? How are you? And again, the pressures produced by a hydraulic head of 2,100 feet are incredible. There's no known example in modern times of ice dammed lakes even coming close to those kinds of pressures. And see, we've got a good example to learn from, because, again, going back to what I said, the Little Ice Age, the glaciers got bigger than they'd been in 10, 11, 12,000 years. So now, 150 years ago, 170 years ago, they start shrinking back. Well, as they shrink back, they're creating proglacial lakes. So throughout the early 19th century, we had an increased number of glacial outburst floods, which is actually diminishing as time goes on, because as the glaciers shrink, the volume of meltwater being contributed is diminishing, and the ability of the ice to form these temporary ice dams is diminishing. In other words, 100 years ago, you might have a tributary valley blocked off by a trunk glacier, right? In the main valley, you've got a big trunk glacier. Okay, but what happens once that trunk glacier recedes above the tributary valley? Well, now the tributary valley is just draining into the main valley. It's not damming up against the ice that's occupying that valley. Does that make sense? Yeah. So we've kind of seen this process playing out on a mini scale during the last 100, 150 years. And we also see that the volume and intensity of these Yokulalps or proglacial outburst floods seems to be diminishing because of the shrinking ice. So what they've said is, well, because they've said that the volume of water has been diminishing. We're kind of getting ahead of ourselves a little bit here, because we're going to dive into the Missoula floods and Channel Scablands in detail upcoming soon, especially when we've already Professor Jerome Lessman of the Vancouver Island University has agreed to be on the show, so he's going to be on coming up in a couple of weeks. And we're going to talk drumlins and some other things, because he is, I would say he probably wouldn't, he's too a humble guy, but I would say he's probably one of the world's foremost experts on drumlins, who is actively researching and studying drumlins at present. I think drumlins are a very important and critical key to deciphering all of this stuff that we're talking about here. So we're going to get into drumlins, and people are going to learn a lot about drumlins because that's part of this vocabulary of hydraulic catastrophes that we're going to be learning about. So underfit streams, that's part of the vocabulary. And what people don't realize is that most of the river valleys in North America are underfit. Most of the modern rivers are occupying huge channels that were created by enormously augmented flows. Now, going back to the southern drainage of Lake Agassiz, Big Stone Lake. I'm going to shift out of the way here. See what I'm doing? Those big stones, those are right at the mouth of the southern tip of Lake Agassiz. And there are fields of these huge boulders splayed out. I'm not sure of the lithology of these boulders yet. They're probably locally derived, but due to their roundness, it does show they've been transported a fairly substantial distance.
Okay, so that's not a whaleback. That's what I was thinking it was. But
no, that is not a whaleback. Those are
boulders.
erratic. Those are flood-deposited erratic boulders.
All right.
We did see whalebacks. Now, whalebacks are where you would have had a bedrock prominence, and you have the erosion on a whaleback can be both glacial, and fluvial. And in fact, there's even a term, glaciofluvial, that encompasses both glaciers and flowing water in its formation. And so whalebacks are glaciofluvial. Got that, Kyle? Let me hear it.
Glaciofluvial.
Glaciofluvial, yes.
Poetic.
Oh, yes.
Yeah, try to use that in a limerick. Probably won't work.
Okay, Russ, that's your assignment for next week.
It takes up the entire
glaciofluvial. I like that term the first time I ever encountered it. Yeah. I think it was like Mama, Dada, Glacio Fluvio. Somewhere in there.
Future geologist.
So, where were we? Normal guy, where were we?
Big Stone Lake.
Big Stone Lake, yeah.
Big Stone Lake.
Because there are big stones there.
That's
Not because
Big Stone Lake is where we wound up at the end of last week's show.
I know. But that's the southern outlet of Glacial Lake Agassiz, Big Stone Lake. Well, I don't think I had this picture. That was the thing. I wanted people to see this picture of these big rounded boulders, because big rounded boulders are another part of the vocabulary. We're going to be learning like new words. It's kind of like we're learning the foreign language here, and each week we're going to add a few more words to it. So we've got these large rounded boulders, which are evidence of rolling and tumbling. Yep. So right here, the presence of these boulders suggests that there was at least the drainage out of Lake Agassiz was apparently not just a nice, slow, gentle affair. Like, there was a river flowing out. Let's go rafting or kayaking down this river. No, these presence of these big rounded boulders here suggest that there was a extraordinarily catastrophic outburst flood from the southern margin of Lake Agassiz. I would speculate that if we look at all those discharge arrows that we were seeing, rather than successional, as the conventional models would try to explain it, well, it was flowing in the southern outlet, then the eastern outlet, then the northern outlet, et cetera, et cetera. What if they were all flowing at the same time? See? And the comment we saw in the quote that we saw, well, maybe the catastrophic flooding into Lake Hind was because of the draining of proglacial lakes upstream. Okay, right. But there again, you see what the problem, I think, is. How far do we take this process to where we get to, okay, here's where it started, right here.
Yeah, they're kicking the can upstream.
Yeah, and they use, it's like a domino process, accepted, like a domino process. The problem is when you got a stack of dominoes up, at some point, somebody has to come in and push that first one over.
Right.
And that's the thing I want to know about. What started that first domino going? See?
Yeah, so we have the painting on the ceiling of the church with God's finger knocking the first domino over. It's obviously what happened.
Obviously. Well, maybe God in the form of, you see what I'm saying? See what I'm pointing at here?
In the form of space, rocks from space.
Rocks from space. Well, yeah, there's some places that we can go eventually. I don't want to go there now because it might get a little bit too esoteric. We're trying to keep our feet on the ground here. But as we get in and learn more and more about this, we're going to see that there's some things that are extremely difficult to explain. And in fact, we really are getting into the rabbit hole here. And so I just want to warn people.
No, that's what we're all here for.
We're all here for the rabbit hole.
That's right.
And normal guy is the guy who's going to be standing up there outside the rabbit hole, kind of feeding down the lifeline to the rest of us. So in case you were wondering, that's what he's doing here.
Oh, that's his job. Yeah.
That's his job. We got to have somebody who's back in normal reality. So if we get too far out, Mike, we're going to be counting on you, man.
So yeah, if you hear us shout evac, start pulling that line.
Okay, so let me get back to some cool stuff here. We're in this map, okay? So there's all the arrows pointing all to the discharge points. We don't see the northern part here. We'll get back to that, though. And then we're going to quickly run through what we saw last week, just so people can get the impression. I want to get these imprints on our mind, what these features look like. Because I would encourage people to get out, take a stroll along the nearest river, the nearest creek, especially after you've had a good, solid, heavy rain. get down there. Don't be afraid to get your feet wet or muddy. Get down there and look at those point bars and start studying the formations on the features. And you know what you're going to see? You're going to see exactly this kind of stuff because it's scale and variant. Now, of course, this is Mars.
Without the craters, right?
Without the craters, right? Right. Without the craters. But these are streamlined forms. Look at this thing right here. What is it like? Isn't this like the perfect shape of a canoe almost? Because what is happening is, when we design canoes and boats or watercraft of any kind, the idea is to reduce friction as much as possible. Now imagine that you've got a watercraft that's square or rectangular. That would be unnatural, wouldn't it? That wouldn't, you wouldn't navigate too well in a square bottomed boat if you're in a current. The idea is, and imagine you've got a blockage in the water and it's rectilinear. It's facing up into this water. The water's flowing. Let's say it's composed of an erodible material, like whatever. It could be anything from soft to relatively hard, like sandstone, let's say. Well, as that water is rushing by it, what of course it's doing is it's concentrating its erosive force on those corners. The corners will be the first to go. Those corners are going to start getting rounded off. And as the water continues to flow, those corners will get more and more rounded, and eventually it'll form almost a parabolic profile looking upstream. Because what it's trying to do is that the water is trying to reduce the frictional resistance of the obstacle to a minimum, right? And so conversely, when you're designing a boat hull, you want the friction of the boat hull moving through the water to be a minimum. So you get this fluviodynamic or aerodynamic shape. So it is these shapes, these aerodynamic shapes that we're looking for in the landscape that are going to be indicators of a fluvial event. So part of this vocabulary we're learning is the SERs, the streamlined erosional residuals, Kyle. But here we see some beautiful examples of streamlined erosional residuals. But these, of course, are on Mars. And we go through here, and here we see the bifurcation, because typically, once you have a main channel that captures the main stream flow, you don't get meandering anymore, especially if it's a bedrock channel, right? But when you have a big channel, see, with a wide, flat floor, and this is very typical of the geomorphic profile of a mega flood produced spillway or channel, is if you'll have a flat floor. And the flat floor is because the water that was running through there is laden with sediment. So when the water begins to slow down, the water will drain off, and you will get these successively more concentrated basal deposits, and then eventually the whole bottom of the spillway or the coulee, whatever the channel, is going to be basically flat. Now you'll have the modern rivers will occupy those channels, right? Because sure, you got a river flowing on the uplands, right? And it's going to be flowing around, but as soon as it hits that channel, and if that channel is 200, 300 feet lower than the uplands, boom, as soon as the river hits that channel and flows in, now it's captured, you see, and that's where it's going to continue to flow. So when the flow goes, it's going to meander, and it's going to be constantly shifting. And it's going to bifurcate, it's going to come back together, it's going to split again, and it's going to create islands, it's going to create these streamlined forms, just like you see here. Here you see multiple bifurcations. Something else I want to start calling people's attention to is this very subtle striations that run longitudinally, that is running parallel to the stream flow, parallel to the direction of the channel. Typically, that is going to be because in these channels, you might have water flowing and there will be sediment. Let's say there's rocks in there, but the power of the flowing water is just not quite capable of elevating and this sediment. And so what happens is that the sediment is moving along the bottom, right? So as the water is flowing, it's moving. Some cases, the sediment may be rolling and tumbling. In other cases, it may actually not even be rotating. It might just be being pushed along the bottom of the water flow. Well, in either case, once the flood is over, that leaves a very distinct morphology on the bottom of the channel, which is this longitudinal erosion, this longitudinal. It might be like ridges with swales. It's very subtle ridges. We'll see many examples of that. Let me, as we go here, down here, you see that bifurcating where the water is splitting and then coming back together. Just another view of the same thing again. So these are the kinds of forms that, look up here. See the streamlining? Look at this thing. It almost, look at a fish. A fish, evolution has created fish to be aerodynamic because they're wanting to move through the water with minimum friction, right? So it's the same principle. Look at this. And again, notice the striations down here that you see, these what we call longitudinal striations that run more or less parallel to the current.
Man, what's all the pockmarking down in the lower left on that one? That's
wild. Hummocky terrain. Now,
Okay,
there's several explanations there. For one thing, that pockmarking, picture that a mega flood comes rushing through and starts ripping up the bedrock.
Okay.
Now you got all this stuff jumbled in, flowing. Now the water, again, because notice here what you've got is that same, notice here you've got a constricted flow and then it opens up, right?
Yeah. So it becomes a sheet flood there. Yeah,
right.
Okay.
Now subsequent floods will come in and mantle that rough-hewn, coarse, bouldery deposits with more sediment. And I think that's probably what we're looking at right here. So we're looking at this tremendous mega-scale outwash debris, and then it's been partially buried under subsequent floods that have mantled it with a finer material. Now here, this is cool, because here you really here you can really see this longitudinal scouring that I'm talking about, these parallel lines. Now, from looking at this, Kyle, which way would you say that the current is flowing?
To the northwest.
Yeah, from the lower right to the upper left.
Yeah.
Yeah, exactly. Pretty obvious, isn't it? You don't have to be a PhD in geomorphology to figure that out.
Look at how many circles there are at the heads of those little striation. That's so crazy. There's little craters at the fronts of the striation marks.
Yeah. And if there's an obstacle in the flow, the flow can create this tail.
Yes.
An elongated tail behind the obstacle.
But I hadn't noticed those tiny little craters, and there are probably hundreds of those.
Yeah. It looks like there's hundreds and hundreds of them. Yeah.
Yeah. I was thinking that, last summer when I was out looking for the Perseids and I was looking up, at the Milky Way, just filling the sky. And I was looking up there and thinking, God, the stars, there must be hundreds of them out there. All right, here we go. Check this out. You see how the striations in the floor of the channel are following the channel? And that is, I would attribute that to coarse sediment essentially being washed along the bottom. But then look at this. Here you've got this meander pattern. You've got it's doing this. See, so that was probably the final, because the water comes in and then it declines, and then there's going to be the final gasp of the floods, the residual flows, and they're going to leave the final subtle imprint right on the surface. They're going to be very superficial, but that will be the last thing that happens hydrologically to the landscape. Beautiful streamlined erosional residual. Now check this out. This is relative dating. We can look at this flood flow that came through here. Which is younger, the flow that cut this channel here or that crater? Which is younger?
The crater is younger.
It has to be, doesn't it?
Yeah, because the rim is in the channel.
So if you had a date on that crater, you would know that the flood that created this channel was older than the crater.
It's also
no, there's one up on the other side of it, straight up, that looks maybe older. Yeah, there's no rim in the channel.
Right, it looks like it's been eroded.
Yeah.
Like this could be a remnant crater that was already there.
Yeah.
When the flood came through, this was afterwards.
It's also interesting that a lot of these channels have no tributary canyons or any apparent
Correct.
water erosion on the cliff edges. So
Right. And that,
whatever flood made this,
and that's
that was
evidence right there that this was a singular event.
Yeah.
It happened. This water came from somewhere. It did its geomorphic work. It stopped, and now you've had a relict or fossilized landscape.
Right.
For the
no
most
more water worked on it. Yeah, that's wild.
It is. So this is streamlined islands in the Mangala Vallis. Check that out, man. I really seriously think we at some point do need to do a podcast from Mars.
Oh, I'm down. Let's do it.
You're down. So yeah, we'll get Elan on the show and see if we can't work out some kind of a deal with him.
Yeah. One-way trip. We can do it.
Elan, we want to do a podcast, a Cosmographia podcast from the surface of Mars. Can you arrange that for us?
Yeah.
Can you get us there and back again? So
we'll test it on Mike, and if it works, we'll go too.
Okay.
Find Corey good.
Have to do what? I missed that.
Yeah, then we could just teleport, right, Brad? And that's what he said.
Oh,
just teleport directly there.
I don't know how they do it.
I'll work on my astral planing.
Thank you, Mike. And well, okay.
Clock's running down, I hate to say.
I hate for you to say that, Brad, because we're having such a good time.
I know.
But check out here the longitudinal scouring. You don't have your hat on yet, but thanks for the warning. Let me hurry up and go through this. Catastrophic flood hypothesis for the origin of the Souris spillway. So, yes, way back in 1982, geologists were looking at this and thinking, catastrophic floods here. And this is good stuff here. Glacial lake spillways in the mid-continent region consist of narrow, deep trenches connecting proglacial lake basins. Geomorphic and sedimentologic evidence from the Souris and Des Lacs spillways in Saskatchewan and North Dakota indicates a catastrophic drainage of glacial Lake Regina. Not just a normal, gentle, predictable type of drainage, but a catastrophic drainage. Then they go on to say later on the same page, modern rivers. Now get this is important. Modern rivers in the mid-continent region commonly occupy former glacial spillways, which connect proglacial lake basins. Some spillways were later utilized by major rivers draining the Rocky Mountains. Glacial lake spillways eroded along the Laurentide ice margin are variable in size, but generally are extremely large relative to most modern river channels. Now, you'd be hard-pressed, in fact, to go into the mid-continent region and find a river that is not flowing in a glacial spillway channel, unless it's a very small tributary river. So let's take a quick look at this. Here is where the basin of Lake Hind was. Here are some of the glacial spillways. A is the Des Lacs. B is the Souris coming down here, flowing back around and flowing into Lake Hind. C is the Moose Mountain spillway. And we don't really see, there's the Assiniboine spillway is coming in up here. We can see it right up here. And then over here is Lake Winnipegosis, and this was where the shore of Lake Agassiz was, right over here. And I've called attention to Turtle Mountain here and Moose Mountain up here. We're going to come back to those because they're very interesting features. In fact, I'll go so far as to say that they are most likely heavily forested, streamlined erosional residuals. All right, so here is from a great old geology, probably one of the first geology books I ever owned, Geology Illustrated by John Shelton, who was not only a geologist, but a pilot and an accomplished photographer. So he had this whole book, Geology Illustrated, and if we're going to have to, we need to start having links to some of these really good sources of people. I think this is still available. You might look it up while you're sitting there, Kyle. Geology Illustrated by John Shelton. But yeah, so this is the glacial Lake Agassiz spillway at the Minnesota-South Dakota border. This is modern Big Stone Lake. So this is the last, as on our tour from Portland to Minneapolis was the last stop here at the bird sanctuary that is in the lake. But you can see here, if you look right here, you see the actual river, the Minnesota River that heads out of Big Stone Lake coming out. And you can see that the Minnesota River right in here is very small compared to the spillway itself, the outlet of Lake Agassiz.
Looks like he took that picture at dawn.
It does.
Practically, yeah.
Yeah. And then here's another one, and you can see how it meanders across the prairie. Here's a textbook example of an underfit stream. Note the diminutive size of the modern stream right in here in comparison to the channel it occupies. This is Cottonwood Slough in South Dakota, a relic of glacial meltdown. And this little creek that you see meandering on the floor here did not sculpt out this spillway. This is a fossil feature that's in the landscape that's on such a huge scale that the modern Holocene forests have pretty much left it intact with very little modification. And then we saw streamlined forms. These are showing up on Google Earth. Now, what's interesting here is that, for generations, people would have lived and worked and traveled over these landscapes without having the slightest idea that when you look at it from another perspective, you see that it's actually a landscape that was created under these outstanding conditions, these outsized conditions. But here you see the fossil streamlining and the bifurcating streams. This is all feeding into the Souris Spillway here. Here's just another view of it. And so you can see here that it hasn't really cut out a channel so much in the sense of a very obvious spillway. But if the flow had continued long enough, and at some point it would have carved out enough of a channel that would have captured the bulk of the water flow. And once that happens, then of course the erosion of the channel itself will accelerate. But see, this is a product of sheet flooding, and it's in the first stage of sheet flooding concentrating into distinct streams. See, so oftentimes you've got a big flood that's coming out as a sheet that's spread out, but obviously, unless it's going over a perfectly flat terrain and the source of the water is perfectly consistent, at some point you're going to find there are high points, there are obstructions, there are low points in the natural terrain, and the water working. Doing its work on this landscape, it will be differential. So a low place might get accelerated erosion. You saw what happens in the lee side of an obstacle. It creates a tail oftentimes. So anyways, I guess my point is that what happens is that what we're seeing here is the first stage of the channelization of a sheet flood. The final stage of channelization will be one of those spillways that you see. And here are two of those giant meltwater spillways converging about 4 miles west of Minot, North Dakota. So here's Souris Spillway coming in, and here's Des Lacs Spillway on the right. This is looking to the southeast, and see where they're converging right here. So again, these are relict features on the landscape. And again, look carefully at the river. Look at the Souris River flowing within this spillway. Underfit river. Well, people can get a sense of the spillways. You're going to see the same phenomena over and over again, where the modern river is diminutive relative to the size of the channel it's flowing in. And the whole mid-continental region is dissected by these massive glacial spillways. And people have been living, working, farming on top of this, for generations without knowing what's under their feet. That there's this whole map of these massive features that were produced by events that were such events to happen on a scale comparable. Again, you could basically figure that all the handiwork of humans that have been imposed upon this continent for the last 10,000 years would be gone in a matter of days. So, yeah, beautiful stuff. And this is the power of Google Earth now that we have this. Whatever you think about Google, like them or not, they still have created an extremely valuable tool that allows us to study geomorphology on a scale never possible to a layperson before. But, yeah, you have to spend a lot of time just immersing yourself in this imagery to start to build up this vocabulary so that you can begin to to visualize and understand the processes at work. Convergence of the Qu'Appelle and Assiniboine River spillways about 5 miles east of the Manitoba-Saskatchewan border. The Qu'Appelle spillway comes in from the right, which is right here, Assiniboine from the left. But you can actually see, if you look over here, notice that there was a distributary, it's called, when a stream flows off the main. When it flows into it, it's a tributary. When it flows off the main flow, it's a distributary. So look, we got a distributary coming here, flowing down. And look, it cut across this island here to rejoin the main flow, and it also continued down this way. And we'll leave it at this. So now we get to some very interesting stuff that we find. These elongated, almost perfectly parallel ridges that are rather mysterious.
That is strange. I see it.
Yeah, notice that this is 13 miles, over 13 and a half miles long. This one right here, the most prominent one. And it's dead straight.
Wow.
What created that? And notice there are other ones over here, parallel. These are not created by, modern humans. Look at this here. So here's an old aerial photograph I was able to find. Check this out. Mysterious linear ridges trending southeastward. Yeah, here's another.
Mark.
Yeah. What do you call it? Say skid marks?
Yeah.
Okay, Brad.
That is wild.
Yeah.
Wow.
And there we go. There's the spillway of Lake Agassiz right there. Lake Traverse. Now, of course, there's a dam right here. So that's why you have a lake. But you can see the little remnant of what the river size would be up here. So this is that outlet. This is where the bird sanctuary is that was such a wonderful place, and where we stopped with Graham, our last stop before we got to Minneapolis.
We keep bringing Graham up. That was an awesome trip we made over 2 weeks in 2014, and I'm hoping we're going to be able to have him on the show to talk about that, because we do keep bringing up some of our little experiences, and maybe even Santha would want to share some of her good time.
Sure. I mean, I actually invited him. I sent him a letter this morning, an email this morning. So hopefully he will join us, and we can talk about Magicians of the Gods, because he's got, I think, 3 chapters in there where he talks about our journey from Portland to Minneapolis and all the things we saw. And he also does a great explanation of giving the background on the controversies in the early days that engulfed Bratz in trying to put forward his mega flood hypothesis. Yeah,
definitely does.
Yeah, very, very good synopsis of that whole episode. And then, of course, I don't know how many folks have read America Before. Excellent book as well. Really raises some interesting things, interesting questions. And as usual, the critics, these critics, their mindset, I don't get it, because they attack Graham just like they've attacked me. Same thing. They don't talk about any of the actual evidence or the facts brought forward or assembled. It's just, like, oh, Graham is he's a reporter. He's not a scientist.
Well, yeah, he's a pseudo-archaeologist.
What does that even mean?
Right.
It doesn't mean a damn thing. It's just a way to avoid, to assume this level of pomposity, of, look, I'm cynical. Look at me. But, here's what I would say. He's a scholar.
Yeah.
He's a scholar. See, he knows about a lot of things, and he's learned a lot in his career and in his life. And does that mean he's got everything right down to the final detail? No. Does it mean he's on the trail of something very profound and a lot of it is right? Yes. Does it mean he might be asking legitimate, valid questions that need to be asked? Yes. So, I've about lost my patience with some of these so-called critics, Well, here's my message to the critics who say, oh, Randall Carlson doesn't have any credentials. He doesn't have any credentials. Let's be clear on something. There's a lot of idiots walking around out there that have credentials. What's important is not credentials. What's important is facts. Got it? Facts. So I try to deal in facts. I'm not concerned about credentials. I've been studying this shit for 45 years, right? So I think at that point, it gives me at least some legitimacy to at least talk about this stuff and raise questions, right? But see, the thing is psychologically, a lot of folks are scared shitless of this kind of information. Because why? Because it undermines their entire worldview. They don't want that. They suspect immediately they hear something and they go, oh, no, there's something in there that's dangerous to my comfortable view of reality. So he has no credentials. Don't pay any attention to the facts. Don't pay any attention to those underfit rivers. Don't pay any attention to those giant erratic boulders, et cetera, et cetera, et cetera. So, yeah, proceed in your ignorance.
Well, the story was for years or 150 years that those channels took millions of years to form, right? Slow. And now we know they formed, some of them practically immediately.
Yeah, and you're not going to find anybody who's going to claim that those channels took millions of years. You're not going to find anybody who claims they took tens of thousands of years. Maybe, there might have been relict channels in existence to some extent, but for the most part, what you're seeing there is the result of catastrophic erosion that occurred within a very short period of time, somewhere between, say, 12 and 14,000 years ago. And you'd be hard-pressed to find somebody from even mainstream scientists now who are going to dispute that. Because, look, all of the guys who've studied this stuff, all of the paleohydrologists and geologists that study this stuff, you'd be hard-pressed to find one that I haven't read, whose work I'm not familiar with. So when somebody comes to me and says, the comments, something like when I was on the Rogan show, well, what do the real scientists say? Well, if you'd shut up and listen, I'm trying to tell you what the real scientists are saying.
That's right.
Get it? Duh. Hey,
hundreds.
Is anybody home up there?
So we're really just getting started on this. So it's going to be exciting to follow through with this for months and months. And RandallCarlson.com is live. It's functioning and it's going to grow. And there's going to be a lot of this information there too. One of the things we're also working on, you mentioned earlier, the glossary, all these terms. We're going to have a section there where you can study up and check these. There's so much to come, but it is live, and we're really excited to make these next steps.
Why don't you mention something about our partnership with HowTube?
Well, we're partnering with HowTube.
Hey, there we go. Well done, Brad.
HowTube.
Yeah, very good. Yeah, that's going to be a pretty cool thing, I think. It's a new platform that's launching, and we're affiliating with it, and I think it's going to help really get the story out. And we like Mike Robertson, the CEO. We've become good friends, and he loves what we're doing and wants to see this story get out to a wider audience. So we've realized that if we form kind of a partnership, that this would facilitate getting this out there to a much wider audience, and plus perhaps open up enough resources, because all of us here are very keen on getting this to the next level of research.
Yeah, and HowTube is a platform that anybody can go to and create an account, and if you have content you want to provide, you can put it on there, and they have a really interesting way of integrating a marketplace into the platform for posting content. So
not just yet though. They've just gotten started. It's not going to be open to everybody. They've got some flagship channels that are going to get started at first. Right. But basically they have been launched at the same time as RandallCarlson.com as with us as the premier channel to get them going. So it is really exciting, and we're still trying to figure out how to best promote it, but there's more channels coming, and it's going to be kind of exclusive, but they've got some really unique features, as Kyle mentioned, with the e-commerce, and it's all about knowledge and freedom and how to do things and education. Right. It's going to be a lot of fun working with them.
Oh, it is. And if anybody listening is really excited about this stuff and you have ideas for content creation, we'd love to listen to it. Because we want to create a forum here that really brings these disparate strands of research and knowledge and investigation from this vast varied array of domains of knowledge, to bring them together. So that's one of our goals here. And if you think you have something to contribute to that, let us know.
Yep.
Definitely.
All right, guys. Great show, Randall. Excellent rant there at the end.
Oh, thanks. Thank you.
I always love it when you trash the scriptards. So. All right, guys. Anything else? Check the show notes for any links.
I'm sure there's a couple more things, but I don't have notes on them, and we're way over time, so I'm good with it. Excellent. But, I will mention, sometimes we'll end up at the same spot, but we've taken a very different route, and we've brought all kinds of new things in, and
that's the idea.
Totally fine.
And really learning, there's superficial learning, and then there's really deep learning. And for deep learning, you have to have iteration and reiteration. That's a part of it, right? And it seems that we're so superficial now. In the old days, you went over stuff and over stuff and over stuff really to get it in. And if you want to learn this language, if you're going to learn a foreign language, you're going to a foreign country. You don't listen to a tape one time and hear the vocabulary and go over there and communicate with the natives. You listen to it over and over and over again. And each time you listen to it, you're adding and building up your vocabulary. And that's what we're doing here. So I don't want to hear any comments about, he already talked about that.
This was a distributary episode, right?
Yes.
We went out and we came back.
You got it. Kyle.
Yeah,
Kyle, you get an attaboy.
All right.
You've earned an attaboy.
I redeemed myself from last episode.
Yeah.
Great job, guys. Enjoy.
All right. See you guys next week.
Good night.
Good night.
Good night.